In part 1 of this video tutorial, we will introduce the quantum model of the atom. Because atoms are too small to be observed directly, we conduct scientific experiments to gather evidence that provides us with a model, a sort of mental picture of how we believe the atom behaves. As technology improves, we collect more evidence to update our model of the atom. Now, I'm going to skip the first few models and go straight to the Ernest Rutherford gold foil experiment, because that's where we start to introduce the concept of the nuclear model, the one that has a nucleus in its theory. Now, if you recall, the Thomson model assumed that the atom was a positive mass with little negative particles called electrons embedded within it. In the gold foil experiment, a radioactive isotope of radium was placed inside a lead-sealed box. There was a small hole drilled inside this lead box that allowed the radioactive alpha particles to come out. Now, these alpha particles are positive charges, and as you know, when two positive charges come close to one another, they will repel each other. In the Thomson model, the positive charges are evenly spread out throughout the atom. Because these positive charges are so spread out, their ability to repel the positive alpha particles that are coming at them is greatly reduced. As such, most of these alpha particles will go straight through the gold foil with very, very little deflection. And when they come in contact with this phosphorus-coated screen, there'll be a small flash to indicate where the alpha particle hit. Now, when they actually conducted the experiment, most of the alpha particles still went straight through, but there was a lot more deflections than they were expecting. And in some cases, the alpha particles were actually reflected back towards the original source. And so Rutherford suggested that the only way for these alpha particles to have such huge reflection angles is if all these positive masses were actually super concentrated in the center of the atom, a nucleus. Because positive charges that are spread out are too weak to deflect the alpha particles with such huge angles. Only a concentrated positive mass can do that. Alright, so let's watch this brief animation to recap what we have just learned.
Ernest Rutherford was bombarding an extremely thin gold foil with a beam of alpha particles from a radioactive source. Alpha particles have a positive charge and are far smaller than an atom. The great majority of particles passed through the foil easily, but 1 in every 10,000 particles was deflected backwards and came back on the same side of the foil. To account for the results of the experiment, Rutherford had to reject the Thomson model of the atom, because if atoms in fact consisted of spheres with a uniformly distributed positive charge, all alpha particles would pass through the foil easily, with some possible minor deflections. Rutherford believed that the center of the atom is a positively charged nucleus, in which nearly the entire mass of the atom is concentrated. The nucleus is surrounded by a virtually empty space within which the electrons circulate. Thus, if a positively charged alpha particle passes at a considerable distance from the nucleus, it passes through the atom easily. However, if a particle collides with a nucleus, it is strongly repelled by the positive nuclear charge and becomes deflected, like a tennis ball hitting a cannonball. Rutherford also concluded that atomic nuclei must be very small compared to the size of whole atoms, if the great majority of alpha particles pass through tightly packed atoms as though they were empty space.
And so the gold foil experiment concluded that the atom is mostly empty space with a very dense, positively charged nucleus at its center. Instead of being embedded in a positive mass, the electrons instead orbited around the nucleus like planets around the sun. Now, before we go ahead, I need to do a quick little detour so we can talk about excited versus ground states. If you can imagine a bowling ball in the air, it has a lot of energy but very little stability. On the other hand, a bowling ball on the ground has a lot of stability but very little energy. Well, similarly, electrons that are far from the nucleus are going to have high energy and low stability, while the electrons that are closer to the nucleus are going to have low energy but high stability. So as the bowling ball falls to the ground, it goes from being unstable to more stable, from a low stability state to a high stability state, or as we like to call it, its ground state. However, that also means that the bowling ball goes from a high energy state to a low energy state. And if you recall, the law of conservation of energy states that energy cannot be created, can't be destroyed, it can only be converted from one form to another. Well, in the case of a bowling ball, the energy just doesn't magically disappear, it's converted from potential energy into kinetic energy, the energy of motion. Similarly, a high energy electron with low stability can become stable by getting rid of its excess energy. As it becomes more stable, reaching its ground state, it also releases energy, but in the form of what? And that's where we encounter our first problem, Newtonian mechanics. So with classical physics, we would expect an excited electron falling back to a ground state would emit a continuous range of frequencies of light. This constant light emission, according to classical physics, would cause the electron to crash into the nucleus and atoms shouldn't exist. But they do. So obviously, Rutherford's model of the atom isn't quite right. To better understand the behavior of electrons, a different experiment was conducted. When we shine a white light through a prism, we get a rainbow effect. But what if we don't use a white light? So this is called a gas discharge tube. Essentially, we put hydrogen gas inside a tube that's been vacuumed out, so there's no other gas inside except for hydrogen, and then we apply an electrical voltage to it. When you apply electrical voltage to it, the hydrogen begins to glow. We use this technology with neon signs, where different gases emit different colors of light. If we take these gases and apply an electrical voltage to them and shine their light through a prism, instead of a continuous spectrum, we see distinct color bands appear. And each type of gas has its own unique line spectra, or pattern of visible light. And that is how we can determine the composition of stars that are light years away from us. We take the starlight, shine it through a prism, and identify what type of light bands are present, because every single element has its own unique light band, as if it's like a fingerprint. To understand this phenomenon, we need to briefly review over the electromagnetic spectrum. In grade 10, you learned that visible light was part of the EM spectrum, along with radio waves, microwaves, infrared light, ultraviolet light, X-rays, and gamma rays. You would also have learned that low energy EM radiation, like radio waves and microwaves, have low frequencies and long wavelengths, whereas high energy EM radiation, like gamma rays and X-rays, have high frequency and short wavelengths. Now, visible light is the part of the EM spectrum that our eyes can detect. Other animals have organs that allow them to see or detect into the infrared and ultraviolet range. So while we would only detect a few patterns in the feathers of this bird, other birds who can see into the ultraviolet range can detect a lot more colorful patterns than we could. Now, the term infrared means below the red, while the term ultraviolet means beyond the violet. So you'll notice in the visible light spectrum, we can see from the red range all the way to the violet range, but just below the red range is infrared, which we cannot detect with our eyes, versus just beyond the violet range, ultraviolet, again, we cannot detect with our eyes. While infrared has a low energy, low frequency, and a long wavelength, ultraviolet has higher energy, shorter wavelengths, and higher frequency. As such, red light has lower energy than violet light. So to recap, when we shine a white light through a prism, we can see all the colors of the visible light spectrum. So every frequency, every wavelength, from red all the way to violet. But when we apply a voltage to a gaseous element, it gives off light, which we can then shine through a prism. But at that point, instead of seeing a continuous spectrum, we see distinct bands of color, specific wavelengths or frequencies of visible light. To explain this phenomenon, Niels Bohr suggested that electrons could only exist in specific, stable orbitals. They could not exist anywhere else. If an electron in a high energy orbital with lower stability falls down to a lower energy level with higher stability. It will release energy, some of which will be in the visible light spectrum. So if we look at this diagram, if an electron drops from the second shell to the first shell, it releases energy in the red wavelength. And as we saw, red is in the lower frequency, lower energy wavelength. But if it drops by 2 shells or 3 shells, it will release energy in the green wavelength or blue wavelength because they are of higher frequency and higher energy. And since every element has its own unique electron pattern, how their electrons release their energy will also be unique, and that of course results in a line spectra that is characteristic to each and every single element on the periodic table. Because electrons can only exist in specific orbitals and not in the spaces between, they can only absorb certain amounts of energy and release those specific amounts of energy. In a third experiment, we shine white light at a cold gas. So if you recall, white light contains all the frequencies, all the wavelengths in the visible spectrum. So we shine and give that energy to a cold gas. The cold gas only absorbs specific wavelengths of energy, specific bands, and those bands correspond to the ones that they emit. So this cold gas will only absorb this specific type of red. Not this red over here, not this red over here, but specifically this red over here. Because if it absorbed too little energy, it would jump up into an area that's not allowed. And if it tried to absorb a different type of red, it may absorb too much energy and end up in a location that is unstable. And so this theory of electrons only being allowed in certain stable energy levels helps to explain why they only absorb specific amounts of energy and why they only release specific amounts of energy. So if you absorb 5 kilojoules of energy to get from here to here, you must release the exact same 5 kilojoules of energy when you drop from there to there. And this is where a lot of physicists at the time were freaking out. How can an electron go from here, a stable orbital here, to a stable orbital here, but not exist in the space between? These experiments prove that electrons can't exist in the space between because there's no energy involved in between the stable points. But this is where we have to accept that the universe doesn't have to make sense, at least not from our perspective. The rules that we make based on our observations of the universe are just that. They are human rules. The universe doesn't have to obey human rules. It does whatever it wants to do. But that's the beautiful thing about science. You don't have to fully comprehend or understand why something behaves the way that it does in order to take advantage of it. Many of our technologies are based upon the acceptance that electrons do not behave the way that we expect them to behave. The rules that govern our world are not the same at the atomic or subatomic levels. But before we get too philosophical, let's try to understand why only certain wavelengths of energy are considered to be stable. Stable wavelengths are those that begin and end at the exact same point. That way they can overlap and reinforce one another, and this leads to stability. On the other hand, wavelengths that are just a little too short or just a little too long do not end up at the same starting and end points. They instead do not overlap, but they will cause an interference pattern. Now I'm obviously exaggerating over here, but you can see how these interference patterns, because it doesn't line up perfectly, they don't reinforce one another, but they will instead start to cancel each other out. As such, these stable energy levels are allowed, while these unstable energy levels are not. So Niels Bohr's model of the atom allows us to explain why every element has its own unique emission and absorption line spectrum, but more importantly, his theories gave scientists permission to think outside the box. Now we have definitive evidence showing that atoms and electrons do not have to behave according to Newtonian physics or Newtonian mechanics. They have their own set of rules, ones that we have not discovered yet, and more importantly, they don't have to make sense according to our worldview. Now another problem that scientists were having a difficult time explaining was called the photoelectric effect, for which Albert Einstein would win his Nobel Prize. Scientists knew at the time that certain materials, when struck with high-frequency energy such as visible light or UV, could eject electrons. This is the basis behind how our solar panels work. So when sunlight strikes the solar panel, it ejects electrons which can then be harnessed to induce a current that goes on to power our electrical devices. Now, at that time, classical physics viewed light as a propagating wave. So a bright light source meant that it was giving out a lot of energy. And if it's giving out a lot of energy, we would expect it to eject a lot of electrons. I mean, that just makes sense. The brighter the light source, the more energy hitting the material. Shouldn't there be more electrons being ejected? But that wasn't the case. What they found was that a dim light source, low intensity waves, could eject more electrons than a bright light source, those with high intensity waves. Imagine having two paper boats in the pond, and then you throw a big giant rock into this pond. You would expect the boat that's closest to the impact site to experience the most intense waves, and the one that's furthest away from the impact site to experience the least intense waves. As such, the one that experiences the most intense waves is the one that's most likely to sink. But not so. With light, it was like having a rock dropped here and doing nothing to this boat, but causing this boat to fly out of the pond. That just doesn't make any sense. Furthermore, they found that blue light could eject more electrons than red light. So it wasn't the intensity or the amplitude of the wave, but rather the frequency of the wave that results in determining how many electrons are ejected out of the material. To explain this phenomenon, Max Planck and Albert Einstein suggested that maybe light behaved like a packet of energy. They called it a quantum of light at the time. Today we call it a photon. So instead of behaving like a wave, light perhaps is behaving like a particle. And so low frequency light has a low quantum of energy. As such, it doesn't have enough energy to dislodge an electron. Because red light is in a low frequency range, it has very little energy. And so it doesn't matter how bright the red light is, each individual photon of red light does not have enough energy to eject an electron. Violet light, on the other hand, is high frequency, high energy. So even if you had a dim light source and didn't throw too many photons at the material, because each individual violet photon or packet of light had enough energy, it could still eject more electrons than a red photon. So trying to eject electrons using red light would be like trying to knock over this brick with ping pong balls. The intensity, or the number of photons I'm throwing at it, is irrelevant. It doesn't matter if I'm throwing one ping pong ball at the brick or 1,000 ping pong balls at the brick. Each individual photon, or in this case ping pong ball, doesn't have enough energy to knock down the brick. So once again, the brightness had nothing to do with how many electrons could be ejected. On the other hand, even one bowling ball can easily knock over a brick. Alright, so it doesn't matter how bright or dim the violet light was, each individual packet or photon of violet light is enough to eject electrons, and that's why violet light could eject more electrons than red light. So, no matter how many photons you throw at the substance by increasing the intensity, no individual photon has enough energy to dislodge an electron. As such, high-frequency light has high quantum of energy and enough energy to dislodge an electron. Einstein and Planck then go on to suggest that light is not a continuous stream, but rather a series of quantized bursts. So from our perspective, light behaves as a continuous stream, like this line over here, a smooth ray. But if you get up close to it, you realize that smooth line is not actually a smooth line, but it's actually pixelated, individual pixels. Similarly, light is not just a smooth continuous stream, but rather a series of quantized bursts, little individual packets or photons of energy. So physical money is an example of something that is quantized. In Canada, we no longer have the penny, and so I must round up or round down to the nearest nickel. I can either have 5 cents or 10 cents. I can't have anything in between. I can't have 7 cents, at least not physically anymore. Similarly, electron orbitals are also quantized. You can either be at this energy level or this energy level, but you cannot be in between these energy levels. Now, the last problem we need to discuss is the wave-particle duality of light. So we have seen how light can behave like a wave, but light can also behave like a particle. But how's that possible when particles and waves are apparently two different things? With particles, Energy and matter travel together. So as this little particle bounces back and forth, energy moves with it. However, in a wave, matter does not move with the energy. So imagine, if you will, a skipping rope. So let's say I'm holding the skipping rope on one end and my friend is holding a skipping rope on the other end. If I wiggle the skipping rope, my friend will feel the energy as it moves from my hand into the skipping rope to their hand. But does the atom in the skipping rope move along the skipping rope? Does it travel from my hand into my friend's hand? No, the atoms in the skipping rope move up and down. Meanwhile, the energy in the wave moves laterally, left to right. So how can light behave like a particle and a wave at the same time? So what I would like you to do at this point is watch the video I've linked to below, specifically at the 14 minutes and 8 second mark through to the 20 minutes and 32 second mark. Once you're done, watch part 2 of my video tutorial.